Hello, welcome to this lesson in the Engineering Mechanics Tutor in Statics. Here we're going to work with this vector in 3 dimensions. So we're given a vector, the magnitude of which is 475 newtons. We're given a couple of angles on the diagram here in 3 dimensions, and we're asked to find the components, Cartesian components, fx, fy, and fz, and to assemble the vector representation here. So we know that we're going to end up using direction cosines, but you have to be really, really careful. First of all, I want to point a couple things out. The way I've drawn this vector on the board is, you see how the dotted lines are kind of set behind the coordinate system? Well, this vector is kind of pointing behind the x and the y axis. So it's almost like in the negative x direction and then also in the negative y direction, but it's got a positive component in z. So that's thing number one that's a little different. All right. Number two is, we have been given the angle from the vector to the z-axis, so we know the direction angle for the z, for theta z. But this angle that's given here, if you notice what's going on here, this angle is 37 degrees, and it's measured between kind of from the x-axis to the projection of the vector down. You see how the dotted line goes down? This vector, if you were to shine a flashlight straight down the z-axis, it would project down onto the dashed line here in the xy plane. Now it's giving us the angle from that projection over to the, in this case, the y-axis. So it's not a direction cosine. This angle here is not a direction cosine. So you can't just plug it straight into a formula for the direction cosine like we did in the last problem. You have to do a little bit more thinking. And it's not going to be quite so obvious. It's not going to be just a single formula to plug into. And that's why I'm doing this problem. I want to tell you, though, that a lot of this stuff, when you read engineering books, especially early on in the mechanics and circuits and things like that, you read it and you think, oh, I understand it, I get it, I'm going to ace the test. And then you get to the test and you realize, whoa, this is not quite exactly like they presented it in the book. That's kind of done on purpose to make you think, okay, to make you think. This problem here gives you 2 angles, and the assumption is a lot of students are just going to assume they're direction cosines or get confused or something and start trying to solve it using formulas that don't apply. You need to recognize that because this angle is not direction cosines, remember, they're measured from the vector to an axis, from the vector to another axis, from vector to another axis. And if they're not measured like that, they're not direction cosines. This is definitely not measured from the vector, it's measured from the projection of the vector into the xy plane. So let me show you real quick. I said a few times already, I'm not going to do this every time, but I want to show you this one because it's kind of neat. Here is an x, y, z representation of what we have on the board. This particular vector, most of the time we have vectors pointed like this, where they have positive x, positive y, positive z. But this one's actually going behind the axis here. Notice that if you think about it this way,